In mathematics, the Coxeter number H is the order of a Coxeter element of an irreducible Coxeter group. It is named after H.S.M. Coxeter. Definitions. Note that this article assumes a finite Coxeter group. For infinite Coxeter groups, there are multiple conjugacy classes of Coxeter elements, and they have infinite order. There are many different ways to define the Coxeter number H of an irreducible root system. A Coxeter element is a product of all simple reflections. The product depends on the order in which they are taken, but different orderings produce conjugate elements which have the same order. The Coxeter number is the number of roots divided by the rank. The number of reflections in the Coxeter group is half the number of roots. The Coxeter number is the order of any Coxeter element. If the highest root is mi alpha I for simple roots alpha I, then the Coxeter number is 1 plus mi. The Coxeter number is the dimension of the corresponding Lie algebra is n, where n is the rank and h is the Coxeter number. The Coxeter number is the highest degree of the fundamental invariant of the Coxeter group acting on polynomials. The Coxeter number is given by the following table. The invariants of the Coxeter group acting on polynomials form a polynomial algebra whose generators are the fundamental invariants. The degrees are given in the table above. Notice that if m is a degree of a fundamental invariant, then so is h plus 2 minus m. The eigenvalues of a Coxeter element are the numbers e2 pi I. H.S.M runs through the degrees of the fundamental invariants. Since this starts with m equals 2, these include the primitive hth root of unity, zeta h equals e2 pi I h, which is important in the Coxeter plane. Below. Group order. There are relations between group order G and the Coxeter number P. 2h Gp equals 1. P, Q, 8, Gp, Q equals 2, P plus 2, Q minus 1, P, Q, R, 64H, Gp, Q, R equals 12, P2, Q, R plus 4, P plus 4, R, P, Q, R, S. 16, Gp, Q, R, S equals 8, Gp, Q, R plus 8, Gq, R, S plus 2, 1, P1, Q1, R1 per second plus 1. An example, 3, 3, 5 has H equals 30, so 64 asterisk 30 per grams equals 1, 2, 3, 6, 5 plus 4 thirds plus 4 fifths equals 2 fifteenths, so G equals 1920 asterisk 15 halves equals 960 asterisk 15 equals 14,400. Coxeter elements. Coxeter elements, if considered as the symmetric group on n elements, are n cycles. For simple reflections, the adjacent transpositions, a Coxeter element is the nth cycle. The dihedral group H.M is generated by two reflections that form an angle of, and thus their product is a rotation by, Coxeter plane. For a given Coxeter element W, there is a unique plane P on which W acts by rotation by 2 pi h. This is called the Coxeter plane and is the plane on which P has eigenvalues e2 pi I h and e minus 2 pi I h equals e2 pi I h. This plane was first systematically studied in, and subsequently used in to provide uniform proofs about properties of Coxeter elements. The Coxeter plane is often used to draw diagrams of higher dimensional polytopes and root systems. The vertices and edges of the polytope, or roots, are orthogonally projected onto the Coxeter plane, yielding a Petrie polygon with h-fold rotational symmetry. For root systems, no root maps to 0, corresponding to the Coxeter element not fixing any root or rather axis. So the projections of orbits under W form h-fold circular arrangements and there is an empty center, as in the E8 diagram at above right. For polytopes, a vertex may map to 0, as depicted below. Projections onto the Coxeter plane are depicted below for the Platonic solids. In 3 dimensions, the symmetry of a regular polyhedron P, Q, with one directed Petrie polygon marked, defined as a composite of 3 reflections, has roto-inversion symmetry SH2+, H+, order H. Adding a mirror, the symmetry can be doubled to antiprismatic symmetry, DHD, 2+, H, order 2H. In orthogonal 2D projection, this becomes dihedral symmetry, Di-H, order 2H. In 4 dimension, the symmetry of a regular polycheiron, P, Q, R, with one directed Petrie polygon marks as a double rotation, defined as a composite of 4 reflections, with symmetry +1, H, CH times CH, order H. In 5 dimension, the symmetry of a regular polycheiron, P, Q, R, S, with one directed Petrie polygon marked, is represented by the composite of 5 reflections.